Welcome back. So I'm really excited about this next sequence of lectures on the numerical integration of ordinary differential equations, because this is where we take a lot of what we have learned so far in how to solve systems of ordinary differential equations, and we kind of move this into much more real-world settings. So we've talked about how to solve linear coupled systems of first-order equations, x dot equals ax, and really these are kind of valid near linearizations near the fixed points or equilibrium of general nonlinear systems. But we haven't talked too much about how to handle a generic nonlinear system of equations, x dot equals f of x, where f is a nonlinear function. Okay, and so linear systems benefit from the fact that linear superposition holds. So you can kind of break this down into simpler subproblems, like you can diagonalize A and solve each of those decoupled problems, and then add those up and get solutions. There aren't generic solution techniques like that for x dot equals f of x for a nonlinear function f. And in those cases, we often resort to numerical integration. So most of the systems we care about, like integrating, predicting the future of a weather system or an epidemiological system or a fluid flow system or even a very complicated mechanical system, typically we can't solve them using these linear techniques, and we have to resort to numerical integration. So that's what I'm going to show you in this sequence, and I'm going to walk you through kind of in this lecture the overview, and then we're going to dive into some topics. So I'm going to talk a little bit more about what I mean by this differential equation, x dot equals f of x. Here, x is typically a vector of the state of my system. It's a vector representing the state of my system, representing the state of my system. It's often called a state vector. That's what it's called. And f of x, f is a function of x, is generically some nonlinear function. It may be a nonlinear function. It may be a nonlinear function. And it might even vary in time. So I've written x dot equals f of x, where f is kind of a constant. It's just a function of x that doesn't change in time. But this function could actually be evolving and changing in time. So that would be an autonomous or a non-autonomous system, would be whether or not this does or does not depend on time. So we'll talk about both of those actually. And one of the examples I like to give of this is, let's say that I have the fluid flow like in the Gulf of Mexico, something like that. So let's say I have, this is Florida, this is the Gulf of Mexico. I'm from, somewhere in Texas over here. And essentially what we have is some fluid velocity field. Sometimes we call this a vector field. So we have some, vector field. I'm just going to draw kind of arrows. I'm making this up. Maybe there is some area of big circulation, right? That's not always a good thing when that happens. Okay, so I've got some big vector field for the fluid flow in the Gulf of Mexico. And let's say I am lost at sea. So I'm like a little, I'm on a life raft or something, and I am at this initial condition, x at time 0. So I not only have this differential equation, I also have some initial condition, x at time 0 equals x naught. And what I might be interested in this system is how to, so first off, this vector field would be f of x. It literally says at every point in space x, what is the vector, the fluid velocity field that is changing my position in time. So I assume that my particle kind of advects or flows along with this, fluid velocity field. And at every point in space here, at every point x, this is my function f of x, okay, is this kind of vector field, velocity field here. And you'll notice that in this example, this two-dimensional fluid flow, my function f has two components. It has the kind of velocity direction in the x component and the velocity component in the y direction. So here, f of a point x would have, some kind of x velocity and some y velocity component. Okay, f of x would have some x velocity and some y velocity component. I'm also going to say that this is not just some function of x, but it's also a function of time. So realistically, I actually should, generically add in this possibility that my function, my right-hand side ordinary differential equation, can be changing or evolving in time. So of course, this flow velocity is constantly evolving in the Gulf of Mexico. It's constantly changing in time because the ocean is churning and wind is blowing the surface and changing things. So this is actually changing in time. And these pink arrows are actually going to be moving in time themselves. Okay, but what I really am interested in is if I have some initial condition x naught, how can I predict where that trajectory is going to go in future times? So can I actually, that's what I mean by numerical integration of ODEs, of an ordinary differential equation, is can I tell where this trajectory is going to go in the future by stepping it forward in kind of these discrete kind of delta t advances in time. So if I know x naught, can I predict what it'll be, one time step in the future? Can I predict what x at time 1 will be? Can I predict what x at time 2 and x at time 3, and so on and so forth? Can I predict a trajectory? So that's what we call a trajectory. I'm just going to write this down. So we say, a trajectory is a path. And I'm really going to say it's some path x of t. Okay, so it's some, it's some path x of t. So this is x of t. But numerically, when I do this on a computer, when I solve this on a computer, what that is actually going to be often is discretized at discrete points in time. Okay, so I'm going to approximate this continuous path with these discrete points, x at time 0, x at time 1, x at time 2, ... all the way up to x at time n. And sometimes if I drop my underbar here, these are still vectors of states, so please don't be confused if I forget an underbar. And so what I mean by a trajectory is typically, I have some x naught, and that's going to be going to some x1, and that's going to be going to some x2, ... all the way to some x n. So that's what I mean by a trajectory, is a kind of either continuous or discrete path of points in time where xk is equal to x at some kth time instance. And oftentimes I'm going to say that these are sampled at a constant discrete delta t. So tk, my kth time instant, would actually be k delta t time steps. Okay, you don't have to take constant time steps, but usually in our numerical integration schemes, we're going to be taking these constant time steps. We'll cook up an algorithm that will step the system forward, that will approximate this true trajectory at these discrete time instances for this differential equation. And again, I'm going to reiterate, the reason we need to resort to numerical integration of these nonlinear ordinary differential equations, like finding a trajectory, evolving in the Gulf of Mexico, is because there is a fundamental limit to what we can do with analytical techniques, with linear techniques, with pencil and paper techniques. Okay, so in really, really big problems or in really complicated problems, these linear techniques are only valid near fixed points, in neighborhoods of fixed points, typically. And it might be really hard to find these fixed points or hard to analyze these for very high dimensional systems. Okay, and so we have to resort to numerical integration for most real world problems of interest. Okay, so in this example, I might want to predict if I'm in some life raft in the Gulf of Mexico. Someone might want to predict based on my last location, where am I going to be a day from now or 2 days from now or something like that. You might also predict where was I last seen. You might actually integrate this backward in time and figure out, okay, well, this is my last, you can integrate these trajectories backwards in times sometimes, and you might do that to figure out where you came from, okay, where a particle or a trajectory came from. Integrating particles in the Gulf of Mexico, is also useful if there is a big oil spill and you want to know where this blob of oil is going to go, 5 days from now, if you want to do a cleanup. And so that begs the next question, and that's something I'm going to talk about in this. So in this series, what I'm going to do, I'm just going to write some of these things out here. So we are going to derive numerical schemes to construct these trajectories, to approximate these trajectories, to approximate kind of x at some next time point xk plus 1 equals some function of xk. So if I know my position at time step now, I want to be able to predict my position at time step at the next time step. So let's say this is xk, and this is xk plus 1. I want to be able to build some numerical scheme, some big F, that approximates a 1 delta t time step forward. So then I can build this trajectory starting from my initial condition by just running it through my numerical scheme. And so some of the numerical schemes we're going to cook up are going to be things like the forward and backward Euler, and backward Euler. I might even derive one of these today in this lecture, backward Euler. We're going to derive things like the Runge-Kutta schemes. These are really, really powerful. So Runge-Kutta, I've heard this pronounced Runge-Kutta. I call it Runge-Kutta. And so there's, second order and fourth order. And so I'm going to talk about these Runge-Kutta schemes, which are kind of the built-in integrators in Python and MATLAB. Very, very good all-purpose numerical integrators, quite accurate. And then I'm also going to talk about advanced schemes like variational and symplectic integrators, advanced integrators. These numerical schemes are called integrators because we are kind of integrating, this dx dt. We're integrating it in time to time step it forward. So then I'll talk about advanced integrators for chaotic systems. For chaotic systems. Because for chaotic systems, you need a little bit more specialized machinery. Okay, so that's one thing we're going to do is we're actually going to derive these different schemes, kind of starting with the very, very simplest, then getting to kind of the all-purpose integrators, and then getting into some advanced integrators if you really, really need advanced capabilities for integrating these trajectories. For these schemes, we're going to talk about specific properties like error properties. We're going to look at the error, and we're going to look at stability. And specifically, I'm mostly going to look at the error and stability properties of these simple Euler and Runge-Kutta schemes, but that's going to build our intuition for more generalized integrators that you might come into contact with later in your research or in your work. So for all of these schemes, we need to be concerned with how accurate is this scheme. If I assume that I have a good estimate of F, how accurate, what is the error for each of these schemes, and what is the stability? Will these actually, are these going to faithfully reproduce my trajectory, or is my forward Euler sometimes going to diverge if I use too big of a time step? That definitely happens, and I'm going to tell you why that happens. Okay, so these are probably going to be 4 or 5 or 6 lectures building on this kind of overview lecture. Maybe I'll have a whole series that I'll add to occasionally because I actually do a lot of work in this numerical integration world. Good. Other things that we care about that I want to tell you about is I like this oil spill example because I think it's pretty intuitive to think about. What if, or maybe my lifeboat example. Maybe I get lost at sea, and there's some report that I was missing sometime around 3 p.m. on Saturday on this beach. Okay, some beach here. And so based on that information, there is some uncertainty in my initial condition and my initial time. And so if I have a little bit of an uncertainty here, so I don't know exactly what my initial condition is, but I have some little, maybe a Gaussian of uncertainty or a little uniform uncertainty, how does that propagate and grow? How does that uncertainty grow as I go forward in time with these different integration schemes? Or if I integrate, my dynamics, even if I integrated this perfectly, how does this uncertainty propagate forward in time? That's a super important question in engineering and scientific applications. I want to know how my uncertainty relates to things like my time step, to the dynamics themselves, whether they're chaotic or not chaotic. I want to know, for what parameter values does this uncertainty grow a lot or a little? Those are very, very important questions, and they're deeply related to this concept of chaos, of sensitive dependence on initial conditions. In chaotic systems, you can get really, really different trajectories, even if their initial conditions are arbitrarily close together. So we're going to also talk quite a bit about kind of chaotic systems and how to integrate and propagate uncertainty in these systems, which is a really interesting, really, really rich area. What else do I want to tell you about? So this function f itself could be the solution of another differential equation or dynamical system. So the vector field f itself, so f may be some nonlinear function. We call this a vector field. We call it sometimes a vector field when we're integrating particles through it, because it's literally at every point in x and every point in state space, it establishes a vector telling you how x changes in time at that point. And so it's a vector field, a field of vectors. And this may be the solution to a partial differential equation. And so actually the continuation of this sequence of lectures in differential equations and dynamical systems, very soon after this, I'll tell you about partial differential equations. So these are ordinary differential equations because they only have a single independent variable, time. But soon I'll tell you about partial differential equations for how this function f evolves in time. So for example, in a fluid flow, f, the velocity field or the vector field of a fluid flow, it actually satisfies its own partial differential equation, which would be something like, the partial derivative of f with respect to time equals some other nonlinear function of f, and maybe its spatial derivatives. So the Navier-Stokes equations for fluid flows can be written kind of like this. So the function f itself might be the solution of another partial differential equation. And so we're interested in this lecture series on integrating a particle through this ordinary differential equation vector field, but that vector field itself might be the solution of another bigger dynamical system, like the fluid flow equations, like the Navier-Stokes equations. Okay, so I just think that's kind of interesting. There's kind of layers and layers of complexity of where you can zoom into these systems. Okay, so we're going to be talking about these different schemes. Probably in the next lecture, I'm going to derive forward Euler and backward Euler and look at their error and stability properties. Then I'm going to introduce Runge-Kutta, and we're going to look at how to code those up, what are their error and stability properties, how do we actually compare those and their properties to these schemes. And then I'm going to talk about chaotic systems and how to propagate uncertainty and integrate, and when you need advanced integrators. Maybe one last thing I'll show you before I kind of go into the next lecture is I'll just give you a flavor for how we're going to be building things like forward Euler and backward Euler. And I think you probably at this point already have a pretty good idea of how to do this. What we're going to do is essentially we're going to take this differential equation x dot equals f of x, and for now we're going to drop the function of t, and I'm just going to say it's x dot equals f of x, and we're going to assume that f doesn't change in time just to make my life easier, but all of this applies to time varying vector fields. What we're going to do is we're going to take our dx dt, and again, remember that this is approximately equal to this finite difference derivative that I showed you in the last few lectures. So what I can do is I can say that my derivative is, so this is x dot, that's approximately equal, so at some time t, the derivative of x of t at some time t is going to be x at time t plus delta t minus x at time t divided by delta t. We know that there's some error associated with this. We can look at the Taylor series of this expression, plug it in, and figure out how much error there is. So this is really only approximately equal to this. But we can use this approximation if we have a small enough delta t, and we can set that equal to f of x at t. Okay? And so based on this expression, I can now solve for x at my next time step in terms of x at my current time step. So I get x at t plus delta t is approximately equal to, again, this is only approximately equal to the right-hand side because this is an approximation of x dot. So x of t plus delta t is approximately equal I multiply both sides by delta t, I add x of t, and I get x of t plus delta t f of x of t. Okay? And so this is the simplest possible numerical integrator to take. If I have x at time now, I can step it forward and get x at 1 delta t in the future. So this is my forward Euler scheme. This is forward Euler, because Euler developed this and looked at these properties. Forward Euler. And so you'll notice that it essentially allows me to do what I want here, which is to build a trajectory. If I have x at time 0, I can step that forward and get x 1 time step in the future at x at time 1. If I have x at time 1, at 1 delta t, then I have x at delta t and I have f of x at delta t. I can get f of x at 2 delta t. And if I have x at 2 delta t, I can get x at 3 delta t and 4 delta t. And I can step that forward and build this integrator. So this is that big f of xk that I was talking about over here. And so sometimes you're going to see us write this as, x at time step k plus 1, 1 delta t in the future is equal to my current time step, x at my current time step, plus delta t f of x at my current time step. And the way we would interpret these subscripts is this means I'm at time tk, or time k delta t. And so if I want to write this out long form, I would say this is x at time tk plus delta t. That's time k plus 1 is tk plus another delta t, equals x at time tk plus delta t f of x at time tk. Okay, so that's how you can kind of go back and forth between these subscript k's and some time, some absolute actual clock time tk. Okay, the kth time that I'm keeping track of. And so this is going to be the name of the game for this whole lecture series for forward Euler, backward Euler, second order Runge-Kutta, fourth order Runge-Kutta, and these advanced schemes. It's super, super simple. At the heart, what we're going to do is we're going to approximate dx dt using some type of finite difference derivative scheme, and we're going to use that. We're going to set that equal to f of x, and we're going to build a scheme to predict x 1 time step in the future based on x now. Okay, so that's all coming up. I'm going to derive all of these, look at their error and stability, and we're going to start integrating, starting with simple systems. We're going to integrate like, a mass on a spring with a damper. So we'll go back to our kind of trusty canonical spring mass damper. We'll integrate a nonlinear pendulum with a large amplitude. So it's not going to, we're not just going to use the small angle approximation anymore. So a large amplitude pendulum. And then we're going to move into chaotic systems like the Lorentz attractor. Let's see if I can draw my Lorentz attractor. We'll get into chaotic systems like the butterfly attractor and like the double pendulum. So the single pendulum is deterministic and it gives you a clockwork of periodic motion. But the double pendulum, where I have a single pendulum attached to another pendulum, these are both chaotic systems. So we're going to build these integrators and test them out on all of these interesting systems. That's all coming up in the next, let's say, 5-6 lectures. I'm looking forward to it. I hope you are. This is going to be kind of the culmination of what we've talked about in ordinary differential equations. We're going to use our intuition for the error analysis. We're going to use eigenvalues and eigenvectors to understand stability of these schemes. And then we're going to take this into the next level of really applying this to hard, real-world, fully nonlinear systems. That's all coming up. All right, thank you.